the stuff that we did last time. And that's not going to work, is it? Let me think. Is that going to work? Yes, that is going to work. Okay. We're on chapter 2, bell-shaped data. It's also called symmetric data, or, symmetric. It's also called normal sometimes. And we talked about what is called the empirical rule. And essentially what that says is that if your data has this nice shape to it, then you can actually, you can understand what percentage of data is in certain ranges. So if you take the mean, which I'm calling X bar, and you go one standard deviation either side of it, we've discovered that about 68% of all the data is in that range. And if you move out to 2 standard deviations, it's 95% of all the data is in that range. And finally, if you move out to 99.7%, that's what you get when you go 3 standard deviations either side of the mean. And so if I just know that the mean and the standard deviation, can't we figure out what percentage of people are in certain ranges? But quite specific ranges, right? 1 standard deviation, 68%, plus or minus 2, 95%, and finally, plus or minus 3 standard deviations, 99.7%. And we also get, as a little added bonus, see the little pieces that are left over at the end? In here and in here, isn't that where the outliers live? So if you're more than 3 standard deviations away from the mean, right, either plus or minus, that means you're an outlier, and we can, that's an important thing to know. And then right at the end, I believe, we did this thing called Z-scores, which was a way to try and compare 2 scores from different data sets, right? So one of them, the mean was 100 and the standard deviation was 50, and the other was, mean of 50 and the standard deviation was 10. And we wanted to, in some way, compare the 2. And what we do is we use what's called the standardized Z-score, which is this guy here. And when you calculate a Z-score, the bigger the Z-score, the more difficult it is to get that score, right? And I think we did the twin story, wasn't it? Where one of them was in one class and one was in the other, and we tried to, they were arguing about who actually did better. And the Z-score is a much fairer representation of difficulty. So, any questions about that quick intro? Do we feel comfortable about most of what's there? Okay, let me see if we can find one. So this is me just going through some practice questions from the homework. This is similar to question 2. The typical amount of sleep. Oh, I think I did that one. Didn't we do the students going to sleep and adding and saying what it was? Yeah. So I'm not doing that one again. Let's do 3 then. This is a distribution for the resting pulse rate for 4-year-olds, and it's bell-shaped. So it's the pulse rate. And resting is, you sit down, little 4-year-olds kind of hard to make them sit down, but imagine you did. And would you look at that? 109, and the standard deviation of typical 4-year-old is 9. I guess when you're younger, doesn't your heart beat faster? I don't know why, but evidently it does, because that sounds to me like a really large number. And the question basically just asks you 3 things. It says, this is the way it's phrased, about 68% of 4-year-olds have a resting pulse rate and then it's your job to basically do from there to there. Right, now if it's 68%, it's the mean plus or minus 1 standard deviation, agreed? 68%, the mean plus or minus 1. So the numbers I'm about to get come from that. Right, so if you take that and subtract 100, you get that. And if you take that and you add, let's see, take away 9, then you add 9, you get that. And then question B, they just ask you the same question, but this time it's 95%. And if you want to find out what range of pulse rates 95% of all 4-year-olds would have, it would be the mean plus or minus 2 standard deviations. So that one would get you 91, and this would get you 127. And just for completeness sake, 99.7% of 4-year-olds, they would have a pulse rate somewhere in this range. So on this side, it would be to 9982. On this side, it would be at 136. And so if you were taking your 4-year-old in for one of those kind of medical checks that you do from time to time on your children, just to make sure everything's developing right, one of the things they might do is check their heart rate, right? And if your kid came in and your child had a heart rate of 150, wouldn't you be worried? Isn't that an exceptionally high heart rate for this type of, for a 4-year-old, right? Or if your child had a heart rate of 70, you would be, you know, the doctor would say, well, that's a bit in the low side, maybe we should check some things here. And if you have any or have had any children, especially when they're babies, don't they do lots of little checks to see if your child is in the normal range, right? So they weigh your child. Okay, your child's 6 months old. This is the typical range for a 6-month-old boy, right? This is a typical heart rate for a 6-month boy. This is a typical, you know, ABC thing. And all those numbers that tell you what's the usual range come from these fellows here. In fact, they might not even use that one. That one would be almost critical. Wouldn't they probably use the 95% one? So if your child had a heart rate of 130, you'd be saying, that's a little bit on the high side. You know, maybe you've just got one of those very energetic kids who's, you know, pumping their heart a lot quicker. And we could do that pretty standard question where if they tell me the mean and standard deviation, you can find the range for these three without too much trouble. So next question we're going to do is calculating some Z-scores. And the first one I can find, it's got a Z score in it, is question 5. The mean weight for men 18 to 24 is 170 pounds. Standard deviation is 20 pounds. Find these standardized Z-scores. So let's find these Z-scores. I'll just pick one at random. Suppose I told you that someone weighed 210 pounds. If you wanted to find out what that Z-score was, it's the data, take away the mean, divided by the standard deviation. So it would look something like this if you wanted to abbreviate it a little bit. We use the symbol S, X bar to represent the mean, and we use just an X on its own to represent the data. So in this case, it's 210 pounds. Take away the mean, which is 170, and divide everything by 20. I want to show you a mistake that you can do when you're doing this on calculators. This might look right, but it's the wrong answer. 210, take away 170, divided by 20. I mean, it kind of looks right, doesn't it? Looks like this calculation. And the answer is 201.5. Now, I know that that's wrong, even if I hadn't done this, because Z-scores typically are in the range -3 to 3. Right, that's what Z-scores are. That's what you typically get when you take the z-score of anybody. They're almost always in the range -3. Getting a z-score of 201 is like winning the lottery every single time for the last 200 years. And even that probably wouldn't be a z-score of 201, right? It's just ain't going to happen. So what was wrong with that calculation? What should I have done?
It divided just 170 by 20. What you should do first is do 210 minus 170, equalize that, and then do divided by 20.
And so the way to fix that is to stick a bracket around it. So that makes the calculator do it once. And now you can divide by 20. And you see that's a much more reasonable score. So in this case, a z-score of 2. And on z-score, just plug and chug, right? You got a formula, just plug in the numbers, chug away, pop out your answer. It's a nice number, but z-scores can be, 2.1, 2, 3, 4, right? Sometimes you're going to round them off, and that's okay when that happens. Are we good with that? Right, now, no side issue, but it's kind of connected to what I said a minute ago. Can you imagine that you had a whole load of data? Yeah, like that. And you have a mean of, I don't know, say 50, a standard deviation of 5, right? So you had a whole load of data, people's ages in a big group at a wedding or something. The average age is quite old, 50, standard deviation was 5. So first all good. Now I could build one of these guys, right? Mean and so on. But I want you to imagine that you found the z-scores of all this data. Try to do it. There we go. So couldn't I find the z-score of 81 and the z-score of 3 and the z-score of 1 and so on? And let's put 50 in the middle, right? First question. What would the z-score of 50 be? If the mean is 50, what would the z-score of 50 be?
Be 0, right?
Yeah. And is it not a truism? Is it not always true that the z-score of the mean will be 0? Right. So if you find somebody who's exactly where the mean was, that person's z-score would be 0. All the numbers that are big, right? So imagine that's in order, including that one. Won't they all have positive z-scores? So if I ask you for the z-score of 52 or 70 or 81, that would be positive. But what would you get if you found a z-score of a number like 1 or 3 or 43? Positive or negative z-scores?
Negative.
Negative z-scores. Now, if you took all of this data and you turned them into z-scores and then you made a graph of it, it would look like that. That wouldn't surprise you, would you? And right in the middle would be 0. And a z-score of 1, 2, 3, -1, -2, -3. Do you see now that when I said a z-score of 210 is phenomenally weird, most z-scores are between 3 and -3. In fact, if you want to think of what is a z-score, one way of looking at it is it's the number of standard deviations that score is away from the mean. So the number of standard deviations that any particular score is away from the mean. So see if that 81 had a z-score of 4. That would mean that 81 was 4 standard deviations away from the mean. Imagine where the mean is and go 1, 2, 3, 4. That's where 81 would live. In fact, if you do z-scores, can you see something that we've used lots of times? Isn't this where the outliers live? Remember the test for an outlier? The mean plus or minus 3 standard deviations. Can you see where that's coming from there? The outliers are the ones that, way out there. 3 standard deviations is 99.7% of the data. 99.7% of all Z scores are within plus or minus 3. And so we can find outliers. We already know how to, but that's kind of where they're coming from. I think that was quite interesting, Let's do another Z-score question. The amount you spend on textbooks in a college student is $560, at least in this one, and the standard deviation is 100. Suppose one particular student spent $500. So this would be question 6. Spent $500. What would the Z-score look for that person? Well, it's data, take away the mean, divided by the standard deviation. So in this case, it would be 500, take away 560, divided by 100, and I can do this one in my head. It's negative 0.6. You get it's a pretty straightforward question, right? Here's a mean, here's a standard deviation. It happens to have a story attached to it. What would the student spend? Well, if this particular student got lucky and spent only $500, that person, we'll assume it's a full-time student. I'm kind of side issue, but I'm nosy. Just to take this class, for instance, I know it's not a textbook, but it's equivalent to a textbook, right? You have to buy something to do your homework and so on. How much does it cost to do WebAssign? I honestly don't know. I'm just curious.
I think it was like $180 or something.
Oh, God in hell, it's worse than I thought it was going to be. I apologize. Now, I wouldn't apologize if they gave me 80 of it, because then I'd think, oh, good, I wish it was more money, but I don't get paid for telling you that this was 180. Ouch. What would a textbook have cost you if you went to the bookstore if we were just doing textbooks?
I would assume around $50 to $80 if you're lucky for a used copy.
This online is a bit of a con, isn't it, for the businesses? You're kind of captive audience because we're doing online, we're doing it this way and it's really the only practical way, unfortunately, doing it. I should have bought stock in that company. They must be making a big profit because they don't even produce a textbook. It's not like a printing press and people working there and, packaging it and posting it out. Don't they just have an online portal? Right.
I mean, yes, but it still costs money to have up servers and such. Now, I don't think they would have to charge that much in order to keep up servers, but I mean, it's not like it's free.
Right. I mean, things cost money, right? And you have to make a profit or else you won't have a company at all. I don't know of many companies that says, oh, we're going to spend a couple of $100 million setting up this company, and then we're just going to lose money for the rest of the day. That would not be a very good business model, but that's a lot of money. I'm sorry for you. But trust me, I've been to university. I know it's a long time ago, but when I went to university, we had to buy quite expensive textbooks. You would be scared, if we converted it into today's money. Aren't there some university textbooks that are well into the 200s, especially if you're buying a textbook that's got a very limited publish, right? If they only publish a couple of thousand. So that's why I guess you have student loans. That's not fun. You've depressed me there. Is there any of your classes that are nice and cheap then to make up for it? No, they all cost you money.
Yeah, I think this is actually my cheapest class, and I spent 140.
Oh, I feel a little bit better now. What would be the worst
Spanish.
class? Spanish is, how much do they, what do they
It gives
cost
you
you?
with a code. The code costs around like 400 something. I remember to get my textbook and code, it was $564.68.
Ouch.
Yeah. or a little green slip of paper that let you hear
Into
some
the class
speak
and do
Spanish.
stuff. Yeah, it'd be cheaper to have a Spanish speaking friend and just learn from them, but I don't think that's the way the college works. Or have a Spanish family, that would be, family who speaks Spanish. That would be even cheaper. Okay. I'm basically just scanning through the homework. The next question, we've kind of sort of done, but there's an extra bit. So I'm going to pretend that this is my version of question 7. It's quite different from theirs. Right, so suppose you were collecting blood pressure again, and the numbers we got were that. We are being asked to find the mean, standard deviation, and a thing called the variance. And the reason I'm picking this question is we have covered it. I think the more times you see something, and the better it is. Isn't this question does not have a solve button, which means you're going to have to do it with your calculator. So here goes. Anybody want to tell me the first button to press?
This is stat.
Okay, and number 1 is edit, and then hit delete button to get rid of the old data. And just type in the numbers in 113, 122, 140, 117, and finally 115. Okay, what do I do next?
Do you hit stat again?
Yeah, but I go somewhere else this time, don't I? Where do we go now? We're on edit. That's the dark thing at the top. But where do I go? Calc or tests?
Calc.
Okay, there we go. And choose number 1 again. And I remember asking this question, so I won't ask it again. And to get L1, it's second 1. And then you hit enter. In this case, the mean is 121.4. And the standard deviation is called S little x, and that's 10.9. And then the guy that we haven't seen. There is another measure of spread called variance. And the variance is simply just the standard deviation squared. So if you wonder what the heck is that, it's 10.9 and you square it. And that answer to 1 decimal place anyway is, whoops, is 118.8. So there are a couple of homework questions that ask you about variance. It's just that guy squared. Hey, no biggie, right? Why do they have 2 standard deviations? Why do they have, a standard? Why do they have 2 measures of spread? One's called standard deviation, and the other's called variance. There are some more advanced uses for variance. They get used in some formula, and it's just easier to call it variance than it is to call it standard deviation squared. It really doesn't make a heck of a difference. Would you agree? If I know that one, I know this one. And if I know this one, I can figure out that one, right? So they're totally interchangeable. They tell the same story in different ways. In some cases, variance is a better measure of spread. It separates out the data a little bit clearer. And that was it. And they call variance S squared, and they call it that because there's another name for standard deviation. So while I'm at this, standard deviation, standard deviation, standard deviation, right? Don't we just have 3 notations that mean the same thing? Thankfully, we only have 2 guys for the mean right now. Later on, you'll find there is another symbol that we use for the mean, and yet another symbol that we use for standard deviation. Remember my story about decimal points? Did I tell you the story about decimal points?
Yeah, you said that. Wait, is it when you told us that decimal points around the world are different, and so sometimes you put yours in the middle?
Yeah. So wouldn't it have been nice if statisticians had got together and just used one symbol for mean and one symbol for standard deviation, right? Too late now, right? Once that happens, you're kind of screwed, so you have to live with the fact there's lots of names for the same guy. So since I'm on standard deviations, here is a couple of puzzle questions that you don't need to actually use your calculator for. You can actually predict the standard deviation or answer the question that's to do with standard deviations by just looking at the data. So here goes. Suppose my data consists of the same number, right? So every single one of them was 10. Would you agree that you don't need a calculator to figure out the mean would be 10? You also do not need a calculator to tell me what the standard deviation is. Remember, the standard deviation is a measure of how spread out things are. So how spread out is that data? Because that's what the standard deviation is equal to.
It'd be 0, right?
It would. Does that make sense? That if all the numbers are the same, there is no variation, right? They're all zeros, right? The different, the spread is 0. Here's another puzzle that, I mean, couldn't you just plug that into the calculator and get those two answers, right? Suppose I tell you that I have a set of data. This set of data, and just for argument's sake, suppose I tell you that the standard deviation is 2. Right? Just pretend that's the case. If I take this set of data and I know the standard deviation is 2, you can tell me what the standard deviation of this set of data is without going near a calculator. What do you think?
2 as well.
Okay. Yes, it is. Do you want to explain why you think it is the case, but why you decided that was the case?
I mean, I imagine you get the same answer when you subtract the data from the mean in both scenarios. So whatever you're dividing by, regardless, because you're starting with the same numerator, it's going to end up being the same
values. Yeah, that makes sense. Here's a just different way of looking at that. Would you agree the only difference between this set of data and this set of data is I added 100? So whatever the first set of data is spread out, haven't you just took the same numbers and just shifted them 100 to the right, but you've kept the spread the same, aren't they? Just the spread out in the hundreds as they were in the original. So that's just my way of explaining that. It makes sense that standard deviation does not care what the numbers are. Doesn't it just care how spread out they are, wherever they are? So these numbers and these set of numbers can have the exact same standard deviation. We good? Right. How about this puzzle story? And this actually is one from the homework. The score in exam that you got, this is your score, was 84. And you know that the mean is 70. Which of these two standard deviations would you like to be true? In other words, you want that 84 to be a really good score in this class. Which of those two standard deviations would a score of 84 be the more difficult to get? I guess that's how I'd phrase it. a standard deviation is 7 or a standard deviation of 18. And all you're meant to do is pick one of them.
7.
Okay. Would you agree if the standard deviation is 7, the data is not very spread out, so won't get in an 84 be hard? Couldn't I double check that by finding out what the z-scores were in each case? So let's see what that would be. If the standard deviation was really 7, then the z-score would be 84 take away 70 divided by 7, and I believe that is 2. If the standard deviation was 18, then the z-score would be 84 take away 70, but now you're dividing by 18, and what does that look like? 84 take away 70 is that, and you then divide it by 18, and roughly it's about 0.8. Isn't that a harder thing to get than that? Do you see it kind of matches what our prediction was? I would want that to be my choice as well, right? Moving on. I guess I should do this because it is a question. There's a couple of questions, and one of them is question 11, but essentially they get you to build one of these guys. And I'll make mine up. So the mean is 100, right? And the standard deviation, let's say it's 5 in my question. So this is very similar to question 11. And what they do is they don't, you can't really it's not easy to draw pictures. So the way they get around it, let me check the lettering, is that guy's called A, that guy is called B, that's called C, this is called D, this one's E, this one's F, and the one at the end is G. And what you have to do is basically just fill in what number each one of these guys is. Right, does that question kind of make sense now? Okay, so won't D be 100? And since the standard deviation is 5, won't that be 105, 110, and 115? Good. And then going backwards, wouldn't that be 95, 90, and 85? Just sometimes it's what they want you to do is the problem, not that you don't know the answer, but you're trying to think, what are all these boxes about? Does that make sense? And they finish with, in a part B, okay, what's the variance of this data? Told you once before how to calculate variance. What's the variance here?
25.
That guy squared. Pretty straightforward question once you figure out what they're asking. And this one is using our table again, and it's a little bit uglier than before. So this is a version of question 13. We're being told that the mean is 58. And we're being told that the standard deviation is 3. And they mention using the empirical rule. Isn't that another name for the 68, 95, 99.7 rule, right? So we really are going to be using that, a version of this guy here. Now, the question that they start off with, these are puzzle questions. What is, this data is head circumferences. So they got a whole bunch of adults and just measured how far round their head is, right? So what is the head circumference, such that only 2.5% of men, because this is male men, 2.5% of adult men have a head have a smaller head circumference. So I'm going to build this guy. Right in the middle is the mean. And then I go 1, 2, 3, 1, 2, 3, right? Adding 3, I get 61, 64, and I'll finish on 67. Taking away 3, I get 55, 52, 49. So far, so good. Now we want to find what score, right? Which one of these numbers would you have to have as a head circumference such that only 2.5% have this or smaller? So I am looking for a guy over here, right? Now, if I do 2 standard deviations either side, what percentage of the data is between here and here? That's 2 standard deviations. What percentage from here to here?
Isn't that like 95%?
It is. And actually, that's not just me randomly picking a guy. If this middle chunk is 95, would you agree that the bits that are left on either side is the other 5%? And would you also agree by symmetry that half on each side makes sense? Do you see how I've split the 5% in? Now, do you notice that that's the 2.5 that they're talking about? Doesn't that mean it's these people in here? So if your head circumference is 52 or smaller, won't you be in the bottom 2.5% of all adult males? In other words, you got a tiny head, son, right? Now, only 2.5% of people have got that kind of circumference. Now, suppose I went and phrased it a little bit differently and said, what is the head circumference such that only 2.5% have a larger head circumference? Wouldn't I be talking about these people, the ones with the big heads? And that answer would have been 64 then. Great. 64. Right. Now, how about question C then? And this time it's head circumference such that only 16% so it's not 2.5%, but they want a 16%. So I guess I could probably do it in this diagram, but it's getting a little bit messy, but I'll try. 16%. Any ideas how that's going to work?
I think it's 61 to 64 because the first standard deviation is 34% and 34% of
Okay,
50
right,
is
hold that thought. I like that thought. So if that 34 that you mentioned is good. So let's see if I can explain where that's coming from, because you must have done something like this. Would you agree 1 standard deviation either side is 68%?
Yeah.
Now, doesn't that split into 2 equal pieces of 34?
Mm-hmm.
And if this bit's 34 and the whole thing is 50, won't that bit there be the 16% that we're doing? Is that your thought process?
Yes.
And that is the right answer. So do you see how that worked? I mean, it's a little bit convoluted. You had to start with 1 standard deviation either side is 68. And then in this question, realize that's 34 and 34. Bearing in mind, you're looking for a 16% over here, aren't you? Well, if that's 34, won't that be 16? You found it. You know it has to be one of these numbers, right? It can't be a number halfway between them, because then it's not really a fair question. I kind of like these puzzle questions because they can be quite different, can't you? You know, if you look at what we did the first time, isn't this just a little bit different? It's in the same ballpark idea, but you know, you get numbers and you deal with them in different ways depending on the story. That kind of question that I've just did, 14 is just like it. It's a similar looking question. And we are now going to enter our last question, which is perfect timing, because by the time we do this, we will have finished that section. So while I'm getting ready, why don't you say your last name for attendance, and I'll get the thing set up. Okay, I'm ready. Hopefully you are too. And here it is, question 15. It says, use a computer, which we will do. We'll use SALT. So the minute I see a SALT button in a question, the chances are I'm going to use it. You know, I would think it a bit strange if I didn't. And this provides a proportion falling below a specified Z-score and determine the approximate proportion. So when you see the word proportion, they're really looking for a decimal or a fraction. Most of the time it's a decimal. So the answer is going to be 0.12 rather than 12%. If they said percentage, this would work as well, but I'd write down 12%. If they want a proportion, I write 0.12. Okay, so that's the difference. Proportion's a decimal, percentage is typically a whole number. Now, this question says the proportion of SAT scores that fall below 430, right? And it comes from 500 as the mean and 100 as the standard deviation. So what this allows us to do is that table that we just finished doing, isn't that only good for set points, 1, 2, and 3 standard deviations? It doesn't let you do the, you know, the between values, you know, what percentage those are. So this will do it for us. And we're going to get a Z-score and an approximate proportion. So I'm going to write that number down because I'm probably going to forget it. This question, the mean is 500, the standard deviation is 100, and they want to be below 430. So you hit the SALT button, and this guy will appear. And there's a guy called the normal distribution. I may have to shrink this out so you can see it a little bit better. Isn't that just another name for a symmetric curve or a bell-shaped data, right? It's just another name. It's called the normal. We know the mean, so I'm going to put that one in, and the mean was 500. And we know the standard deviation, and the standard deviation is this one. And we want to find below. Now, they have funny names here. Left tail, you see it takes everybody below. Right tail, doesn't that take everybody above? So if I wanted to know what proportion was bigger than 420, I would use this, bigger than, more than. I want a less than, so left tail. And I want to do less than, so we fill it in here. And the answer was 430. Okay, so you want to know what proportion of people from this data set would have a score less than 430? The answer, in this case, is that number there. Do you see the proportion? You probably round it off to 0.24. Let's make that a little bit bigger. We don't need the picture now. I want to see the numbers. There. And guess what? There's your Z-score as well. If I wanted to know what proportion of the people or the data was bigger than something, I choose the right tail. And you see a little greater than, and let's suppose I was interested in the proportion that were bigger than 521. Can you see the little shading? Well, roughly, isn't that about 41, 42% of the people? How about bigger than 600? Well, that's what, about 15, 16% of people. How about bigger than 800? Can you see that's almost nobody? Right? 0.0013 is about 0.1%, right? 1 in 1,000 people would have that kind of score in this particular story. So isn't that kind of cool? You can find bigger than, you can find less than, you can actually find between. Let me click on it. You want a between? I'd like to know how many people have a score, right, that's bigger than 550 and less than 420. I got it wrong. No, I got that right. It's only 420. What are you doing? Oh, it reset it. I didn't realize that. I'll do it between. There we go. Okay. I want you to be bigger than 420 and less than 550. There we go. Right, I got it back to front. Right, small guy to big guy. That makes sense, right? For between, and that's about almost 50% of the people, aren't they, in that range? So that's a cool little piece of software, isn't it? That it can tell you what percentage of your data from one number bigger, one number less, or betweens. And that is us for today. I'll hang about for any questions. Otherwise, I'll see you tomorrow. We learned some cool stuff today, didn't we? See you tomorrow. Haley, do you have a question for me? Okay, I'll assume that you forgot to log off.